Let's talk about esters. So, our way of making esters that's important here is the Fischer esterification, which is acid catalyzed. And since this mechanism is one that follows our exact acid catalysis mechanism that we've looked at the beginning of this chapter, I've already got it written out for us, so we can just go over it. So, because this is acid catalyzed, first step is protonation. In this case, we want to limit the amount of water present because this is all equilibrium. It will all go backwards. So we want to have as little water as possible. So with this, you'll have your protonated alcohol as your proton source. It's going to go ahead and get a proton onto the carbonyl. Next step, the alcohol attacks. Then we have a deprotonation step afterwards. And then, or really, it's going to be a proton transfer because right after that, one of the hydroxy groups will grab a proton off our protonated alcohol, which had just functioned as the base previously. We have the carbonyl closing down, kicking out water as a leaving group, as we'll see later what to do about that. And then we have in the last step, the deprotonation, where we're going to reform our catalyst, and we made our ester. The water, since it can undergo hydrolysis, esters and the water and the alcohol are pretty similar, right? So we want to remove the water. One way to do this is using a Dean-Stark apparatus. Typically, you'll have a solvent that is able to trap that water, like toluene is. You'll have your vessel under heat. That's my fire. It's beautiful. As the solvent and the water and the alcohol all condense or evaporate together, they will be condensed in a separate area. Typically, you want a nice hydrophobic solvent like toluene, which then will separate from the water. If we kind of zoom in there, if we zoom in what's happening at this stopcock, we'll see that we'll have a separation happening because water and toluene are immiscible. They do not mix. So toluene is very nonpolar. Water is very polar. They will be immiscible together. So we'll end up separating those. And toluene being less dense than water, the water will sink to the bottom. At that point, we can drain out our water by opening up that stopcock, allowing the water to go out, and then leaving our toluene. We make sure that this doesn't lose all the solvent because eventually all the extra condensate will come back and go right back into your solution. So you're able to remove the water this way. Another way is what are called molecular sieves. Sieves, rather. I don't know why I said sieves. But they're just little like pasta-looking things. And if we like zoom in, they have these little holes in them that are just the right size for a water molecule. And so the water molecules kind of get trapped in them. And so it just physically traps water. And so if you're going to do the Fischer esterification, you really want to use a great excess of your alcohol and then one of these water removing mechanisms, because the hydrolysis of the ester will happen otherwise. So to kind of sum up what we're looking at here, we have our acid. In this case, I've used acetic acid and ethanol, but you want to use a great deal of alcohol. You want to use your acid catalyst and heat. And in doing so, you'll also want to remove water. So you'll use a Dean-Stark trap or you'll use molecular sieves. You don't need to worry about that. I used to make students worry about putting that as part of their reaction. I'm not going to do that anymore. But you'll see in some of the practice problems that I'll say Dean-Stark. That's what I mean. It just is there to remove the water. And you'll get your ester out. All right, so with that, that's the general idea. Of course, then, as we know, since this was entirely equilibrium, if we wanted to get rid of the ester, because we just spent all that time making it, we can do the exact opposite. Put a lot of water, acid, heat, we will go back to the acid. The mechanism for this is exactly the opposite. Or we can say it's exactly the same. Just switch the H and the R group on your alcohol. So make this into the R, and make this R group here into an H. And do the same thing for the rest of the mechanism, and that's the mechanism. So everything is just switched. And that's how we'll hydrolyze. So happens pretty readily. So esters are acid and base sensitive, as we'll see. Speaking of which, if we treat an ester in basic conditions, if we use NaOH, water, we'll get our carboxylate out. And if we want to protonate that, we're going to need a base. We're going to need an acid wash later. So right now we get the carboxylate, and I want to stop here. If we really wanted, yes, use some acid wash, you can get your carboxylic acid again. But the carboxylate is important because this is how soap is made. Fats are esters. They're esters of glycerol, right? We know they're triglycerides. You'll have 3 esters with long chains of carbons on them. And in the presence of sodium hydroxide, or lye, as it is known by the layman's terms, you'll make the carboxylates out of those. And we'll see that those are soaps. Long R group carboxylates are soaps. Sodium soaps, sodium carboxylates tend to be the hard soaps, the bars that you see. Potassium ones tend to be the soft soaps, the liquid soaps. So you can kind of tune that. This process is called saponification, which means soap making. But really, it's just base catalyzed hydrolysis of esters. So there's one very industrially important way of doing this. So back in the day, in medieval times, they would boil pig fat, or called tallow, and with potash, which is potassium carbonate, and which is a base, right? We're using sodium hydroxide because it's a much stronger base here because we have access to that. But they would use a milder base, but it would still work, and they would end up with these soaps. So that's how soap used to be made. It's still made the same way, although we typically don't use animal fats as much anymore. We tend to use plant fats just because they're a lot easier and more environmentally friendly. So we can make soaps, hooray! Which are long chain carboxylates. So that's kind of it for esters. Again, we can do the same sort of last things. We can reduce them if we were so inclined. If you use lithium aluminum hydride, you will get your alcohol out. In this case, you can't use the fancy lithium aluminum hydride. You're not going to be able to get the aldehyde out. All right, the ester is simply not reactive enough to get the aldehyde. And the same thing with the Gilman. The Gilman is not strong enough to react with the ester. But Grignard can completely destroy your molecule. You'll end up getting, again, the alcohol with 2 more R groups added. So with that, you can do those. You'll also need the water in the second step for both. But no Gilman, no fancy lithium aluminum trialkoxyhydride. So ester is a little bit less reactive, but we see some of the same reactions here. All right, and then we have 2 more groups left. I guess we have acids as well, so 3 groups left. We have acids themselves, which we've really seen all of them so far. We can make esters out of them, or acid chlorides, or anhydrides. Or carboxylates, right? We've seen all those. So we have amides, acids, and nitriles left, and we'll look at those next.